Hi, my name is Sandhya Kumari, Assistant Professor from the Department of ECE, Siddhartha Institute of Science and Technology. So, today we are going to discuss about the subject signal systems and random process. So, in this, we are going to discuss about Fourier transform and what are the advantages of Fourier transform and compare it to Fourier series, and so how we can derive Fourier transform from the Fourier series. So Fourier transform. So here we are going to learn about Fourier transform and Fourier series. The Fourier series disadvantage is only applicable for periodic signals and it won't applicable for aperiodic signals. So that's the main disadvantage of Fourier series. The Fourier transform is the extension to the Fourier series where it is applicable for both periodic and aperiodic signals. This Fourier transform and Fourier series was invented by the scientist Fourier. So who defined this algorithm as like a mathematical model, which is applicable for both signals, images, and for multi-domain applications. So this Fourier transform and Fourier series is helpful to analyze a real-time signal or any complex signal. So into a simple components of the signal. Like we can analyze, if you are having a complex signal, we can analyze that signal by partitioning into the sum of some some of the partitions like individual components of the signal. By taking the individual components of your real-time signal, you can analyze the complete representation of a signal. So the disadvantage of Fourier series is only applicable for periodic signals. So to avoid that challenge, so Fourier invented a mathematical model. So to create signals between time domain to frequency domain and frequency domain to time domain. So which is also defined as a Fourier transform. This Fourier transform has many applications like multi-domain applications in physics, engineering, and analyzing linear time invariant systems, radar, astronomy, signal processing, image processing, etc. So here you can see the derivation part, how we can derive Fourier transform from Fourier series. The complex Fourier series representation of f of t is f of t equals to summation k equals to minus infinity to infinity a suffix k e power j k omega naught t. Here, a suffix k represents the coefficient of your signal. So in analyzing a complete representation of a signal, so it is mandatory to know the coefficients of the signal. So by analyzing the coefficients only, we can get the knowledge of what are the characteristics of a signal. So how the signal varied, or what are the frequency components of the signal after applying the Fourier transform. Then let 1 by t naught equals to del of f. So it represents 1 by t equals to the frequency. F of t equals to, just substitute that 1 by t naught in the above equation. F of t equals to summation k equals to minus infinity to infinity a suffix k e power j 2 pi k del ft, where it is represented as a equation 2. Then we can get the coefficient as a suffix k equals to 1 by t naught integration of t naught to t naught plus t, which is a time period. So f of t into e power minus j k omega naught t dt. So where a represents the coefficient value of a signal. So these are the a coefficient of a signal. By to analyze the overall Fourier transform of a signal, so these particular coefficients plays a crucial role in analyzing the Fourier transform of a signal. And by substituting this a suffix k or the coefficient value in the above equation 2, then you can get the final equation as f of t equals to integration minus infinity to infinity f of omega into e power j omega t d omega, where f of omega is your Fourier transform parameter. F of omega equals to integration minus infinity to infinity f of t into e power minus j omega t or j 2 pi t dt. So the Fourier transform of a signal is represented with the parameter f of omega, and the inverse Fourier transform of a signal is represented with the parameter f of t. So f of t equals to integration minus infinity to infinity f of omega into e power j omega t d omega. So here some of the examples or some of the Fourier transform of standard signals. So here Fourier transform of a gate function. So you can see the signal representation of a gate function. Next, Fourier transform of impulse function. The Fourier transform of impulse function is, so these impulse functions you can substitute in the Fourier transform equation as f of omega equals to integration minus infinity to infinity f of t into e power minus j omega t dt. Here in the for impulse function, so here f of t is your del of t. So if you substitute the del of t in the place of f of t, so you'll get the value as 1. So finally, the Fourier transform of impulse function is 1. And the Fourier transform of step function. So E of t is the time domain representation and U of omega is the frequency domain representation. E of omega equals to pi into del of omega plus 1 by j omega. Next, the Fourier transform of exponentials. The Fourier transform of exponentials are e power minus a u of t and e power j omega naught t equals to del of omega minus omega naught e power minus at into u of t. So if you apply Fourier transform to this, you will get 1 by a plus j omega. Next, Fourier transform of signum function. Signum function is, so as gn of t. If you apply this Fourier transform to this signum of t function, you will get 2 by j omega. And here's some functions and with function time domain and frequency domain. So here's a set of common functions that are used in Fourier transform. So direct, delta, constant, cosine function, sine function, unit step, rectangular function, sinc function, form function, Gaussian function. So under all this, so cosine function, sine function is the most repeatable functions. So cos function, as if you apply cos function to the Fourier transform, it can be represented as del of f minus f naught plus del of f plus f naught by 2. Sine function as del of f minus f naught minus del of f plus f naught by 2z. And the sinc function is 1 by mod a rectangle f of f by a. And Gaussian function as e power minus alpha t square. So if you apply Fourier transform, it can be represented as del of square root of pi by alpha e power minus pi f whole square by alpha. So the magnitude and phase response. So the magnitude and phase response of a signal can be plotted in MATLAB. So which you can say the mathematics laboratory. So for any real-time signal, it's mandatory to analyze the magnitude and phase response of it. So the magnitude represents the amplitude characteristics of a signal and phase response represents the angle of a signal. So which is these both parameters is used to analyze the complete transformation of a signal. Here, the magnitude response of a signal can be represented as says x of omega. So x of omega equals to is a combination of real part and imaginary part of a signal as x or of omega plus j xi of omega, where x or of omega equals to real part and xi of omega equals to imaginary part, and the magnitude as mod of x of omega equals to square root of x of omega square plus xi of omega square, and the phase of a signal can be represented as tan inverse of xi of omega by xr of omega. So this magnitude spectrum also defined as amplitude spectrum of a signal. The magnitude and phase spectrum together can represent as a frequency spectrum of a signal. And these are the references that I have followed for this presentation. And these are the web references. Thank you.